Now that we have our equation for the kinetic energy of an object, let's talk about the potential energy of an object, and then we will talk about how to relate and trade back and forth between kinetic and potential energy. Okay, so gravitational potential energy is energy stored by an object being in a gravitational field, and in general we expect that the higher off the ground an object is, the more energy we are storing, because the higher I drop an object from, the faster it will be going when it hits the ground. In order to calculate the amount of potential energy could be stored in an object, let's consider how much work gravity does when we drop an object. So, let's imagine that I have a pen and I drop the pen. So, looking at the forces, after the pen is dropped, the only force on that object is the force of gravity, which is of course mg. All right, we'll just make down positive because the pen's moving down. And work only cares about the direction of your force relative to the direction of motion anyway, so it doesn't really matter. Okay, so I have a force applied downwards, and again, let's say that I drop it by some height h. So I drop the pen, say this is the ground. So I drop the pen some height h off the ground, and I want to see how much work gravity has done to the pen by the time it hits the ground. All right, well, my work equation is once again the magnitude of F multiplied by the magnitude of D multiplied by the cosine of the angle between the two. Well, the force of gravity is just mg. The distance that we dropped is just h. And the cosine of theta here, well, the force of gravity points down, and the displacement also points down, which means there's a 0-degree angle between those vectors. And we can just remember that the cosine of 0 is 1, which means that the work done by gravity here is mgh. The work should be positive because the force is in the same direction as the displacement, and it has a magnitude equal to mgh. That is the mass of the object multiplied by the acceleration due to gravity multiplied by the height through which it fell. So what we're going to do is we're just going to call this amount of work that gravity is able to do on an object the potential energy of that object. So we'll just say that the potential energy, that is the work that gravity could do on that object, is equal to mgh. Mass times gravity times the height of the object. And that energy, when the pen is sitting here, is stored in the pen, right? Making it potential energy. And as soon as I drop the pen, I get that energy out. I release that potential energy, which turns into kinetic energy. Okay, so let's see why this is such a useful concept to think about. Specifically, let's do an example where we have some potential energy and we transfer it into kinetic energy. All right. So, I'll write our PE, I'll make it PE sub G, potential energy due to gravity, mgh. All right. And let's just think about this pen. Let's make it 2 meters off the ground. And let's make it a 10-kilogram pen. And what I want to do is I want to find its velocity right before it hits the ground. So I want to find V final, the velocity of the pen just before it hits the ground. All right. Well, to do this, we need to know our relationship between energies at various points in the system. And the way that we do that is called the work energy theorem. The work energy theorem says that the final energy, E sub F, the final energy of the system, and by system, I just mean the object we're paying attention to. So in this case, the system is the pen. The system could be you or a box or a glass, any object that you're interested in. So instead of system, you could say object. The final energy of the object is equal to the initial energy of the object plus work done by non-conservative forces. So this is work. NC stands for non-conservative. And in our case, work done by non-conservative forces really is only going to mean friction. Friction or you pushing or pulling. So me pushing the pen up into the air, that is a non-conservative force. Friction, slowing down an object as it's sliding, that's a non-conservative force. The things that are not non-conservative, i.e. the things that are conservative forces in our case are going to be gravity. So if it's gravity, then it counts as a potential energy and not a work in our equation. Otherwise, if it's friction or you pushing or pulling on an object, we have to count it here. Okay, so that's what non-conservative work means. But in the absence of that, and in dropping our pen, we are ignoring friction and air resistance and any kinds of non-conservative work things, that term is going to be 0. Often, but not always, the non-conservative work term in our work energy theorem will be 0. So without that term, we just get that the final energy of our object equals the initial energy of our object, and that's what we're going to work with here. So we know in this case that the work done by non-conservative forces is 0, which means that the final energy of the pen must equal the initial energy of the pen. And this is where the beauty of energy comes in that we can take the final energy, the energy of the pen right before it hits the ground is going to be all kinetic. So we can relate the amount of kinetic energy that the pen has right before it hits the ground with the amount of potential energy in gravity that it had right before we dropped it here. Okay. Let's see how this works. To start with, whenever we're doing an energy problem, the thing we want to do is we want to write down our initial energy in terms of types of energy that we have. So we will start by writing energy initial equals the initial potential energy plus the initial kinetic energy. So that is just mgh initial plus 1/2 mv initial squared. Now, in this case, we said we dropped the pen, which means that its initial velocity must be 0, which means that this term here must be 0. So we can write that our initial energy equals mgh initial, our height that we dropped the pen from. Okay. So now we've written down our initial energy. Let's try to write down our final energy. Well, our final energy is our kinetic energy at our final point plus our potential energy at our final point. Well, that's 1/2 mv final squared plus mgh final. But our height, when we are just about to hit the ground, is 0, right? H final is clearly 0 when we're right on the ground. which means that this term here is 0, and our final energy is just 1/2 mv final squared. So now what we can do is we can relate, using our work energy theorem, our final kinetic energy to our initial potential energy, which we will do right down here. So E final equals E initial. That's 1/2 mv final squared equals mgh initial. And note that the masses cancel out, so that's nice. We didn't actually need to know the mass of the object. And if we solve for V final, we get 2gh initial, and then we square root both sides. Now, this result should actually look very familiar from our kinematics section. That is, if we solved this problem, because we know how to solve this problem using just kinematics, we would expect to get the same result, right? So why don't we double check our energy solution, where we took our initial potential energy and set it equal to our final kinetic energy, and then solved for our final velocity. Why don't we double check that using our kinematics? So here, if we're going to do kinematics, we know that we're dealing with only our y direction. And we first, in doing kinematics, list all of the variables that we know. Well, we know v initial y is 0 because I dropped it. We know y initial is h initial, which is 2 meters. We know y final is 0. And we know that the acceleration in the y direction is g. We'll use a coordinate system where down is the positive direction and keep g as a positive value here, just for simplicity. Okay. And we know that we are looking for v final. That's our goal. And I'll say v final y because we're dealing with x and possibly y. Okay. Well, now we need to remember our kinematic equations and figure out, is there a kinematic equation where we can know the initial height and the acceleration and find v final? And luckily there is. It is v final squared equals v initial squared plus 2a delta y. We know that the initial velocity in y is 0, which leads us to vy final equals 2a. Delta y is y final minus y initial, which is, oh, sorry, I should make this negative. Yes. By making y initial a positive value and making y final 0, I said that moving in the positive direction is increasing my y value, so I need to make up positive. All right, sorry I missed that. So in making up positive, I need my acceleration due to y to be a negative value, negative g. So I can say that this is 2 times negative g times y final minus y initial. So 0 minus h initial is negative h initial. And this is squared. 2 negatives make a positive, and I get v final y is square root of 2gh initial. Hey, look, it's exactly the same thing that we found using energy. So we were able to use our kinematic knowledge and find exactly the same value here. Now, you're probably thinking, I already know how to do this, and I spent a bunch of time doing this, and I got the exact same answer that we used this brand new method and introduced these concepts of work and energy in order to get exactly the same result as I had before. That is true. The beauty of work and energy is that work and energy are all scalars. They don't have direction, and therefore you don't actually have to break them up into X and Y. And it doesn't matter if you are moving in X and Y or both, or in some very complicated path. You can just calculate energy and energy conservation. So in a simple straight line, projectile motion or work and energy are effectively equivalent and lead to the same result. But now let's try an example of the same thing where we see that the kinematics section is harder and we are able to very quickly get a result using work and energy. Now what we're going to do is we are going to look at the situation where we have a mixture of kinetic and potential energy. So now let's imagine that we have a block that is 2 meters off of what we're going to call the ground at this level here, that is moving at 3 meters per second. And the block moves down this ramp and out, and what we want to do is figure out its velocity when it is over here. Now, first, let's just think about if we had to do this using kinematics. Well, we know how to do a block on a slope if it's a consistent slope. If we have a block that is sliding down a flat slope, we know how to deal with that situation. But if we have a block that's on some kind of a curve, the angle of the slope is constantly changing, and we actually don't know how to deal with this at the moment. And in fact, without knowing the exact details of the slope, you actually just can't solve it. You would need to know every single detail of how the slope moves in order to be able to solve it. And even then, it would take a lot of mathematical headaches to get a solution to the velocity of the block moving down some kind of a curved ramp. But with energy, we don't care what the curve looks like. Because energy is a scalar, it is just a value, all we have to do is be able to assign a energy value to the block as it is moving along. And because there's no friction, there's no pushing, there's no pulling, we know that the block has the same energy at all points. That is, E final equals E initial plus work done by non-conservative forces. Again, this is friction or you pushing or pulling on the block, but we don't have any of those things, so no work is done by them. So E final equals E initial, which means that if we can figure out the energy that this object has at any point, we know the energy at every point. And if we can just figure out the ratio of kinetic and potential energy at that point, then we can figure out its kinetic and potential at every single point. So the first step that we do when we are looking at a problem like this is we try to find the initial energy to see if we can find a value for the initial energy. As long as there's no work non-conservative, once you know initial energy, you know final energy, and we can go from there. So the initial energy of my block is going to be the initial potential energy plus the initial kinetic energy. Well, in this case, my block is moving, so it must have kinetic energy, and it is off of what I'm calling the ground, so it must have potential energy as well. So I know that it has some mgh initial plus some 1/2 m v initial squared. And because I know h initial, 2 meters, v initial, 3 meters per second squared, I can calculate the initial energy up to a value of the mass. And so that we can actually get a value here, I will give us a mass of 10 kilograms. So our initial energy with a mass of 10 kilograms is going to be 10 kilograms times 9.8 meters per second squared multiplied by 2 meters plus 1/2 times 10 kilograms multiplied by 3 meters per second squared. So this is 98 times 2 is 196. And because energy is related to work, it must have the same units as work, because energy is equal to work. We found all of these energies by looking at work. It must have units of joules. So my initial energy is 196 joules of potential energy, plus 50 times 9 is going to be 450 joules of kinetic energy. Now, adding these two things together, we get 646 joules of total energy for my block. 196 of it is potential energy due to the block being high off the ground. 450 joules of it is kinetic energy due to the block moving at 3 meters per second squared. Okay. Now what we can do is we can use this value for initial energy to find out about the final energy. So let's pick a final point that we're interested in. Let's say here. Okay. Well, when my block is here, I know that it has some velocity to the right, and I know that it is at what I have called h equals 0, and therefore it does not have a potential energy. So, E final is going to be PE final plus KE final, but I know that my potential energy final is 0 because I'm at the point where I said h equals 0, which equals 1/2 mv final squared. And because E final equals E initial, this must equal 646 joules of energy. Now all I need to do is solve for V final, right? V final is going to be the square root of 2 times 646 joules divided by 10 kilograms, which is a value that you can get in your calculator. So this problem is not something that we could have solved with kinematics, with our normal kinematic equations, because we don't know about the angle of the ramp at every point. But with energy, we just don't care. As long as there's no friction, we don't care what happens in between. We only care about how much energy did we start with, and we know that that's the amount of energy that we end with.